At this point, we can define block codes, and these are based on encoding and decoding functions defined in these sets, and these denotes a set of binary numbers, and 2 here denotes 0, 1. You have 2 elements in your alphabet, and n here denotes the length. So these are the set of, this is the set of binary strings of length n, and this is the set of binary strings of length m. So my encoding function takes an m-bit string and turns it into an m-bit string. So of course here m should be greater than n, so that I'm adding some redundancy so that I can detect any errors or hopefully correct them. And we also have the decoding function, which is essentially the inverse function. A code word is any element in the image of E, meaning that any legitimate message encoded, whatever the result is, we call it a code word. Clearly, this has to be a one-to-one function to avoid ambiguity in decoding. Assume that X and Y are code words, elements in this set. We call the concept of Hamming distance here the difference between bit positions, the number of bits in which these two code words, X and Y, are different. Okay? Alternatively, you can express it in this way. Again, addition here is the addition in the Boolean ring. So it's effectively an XOR operation. Okay? So for instance, 0001 and 1010, these are, let's say these are two code words, and their Hamming distance is they differ in this bit, they do not differ in this bit, they differ in this bit, and they differ in this bit. So the Hamming distance between these two is 3. Now, the minimum distance, dmin, of a code is the minimum of Hamming distances between all pairs of possible code words. Whatever your code is, you have a list of code words that are legitimate messages, and you compute the Hamming distances between all possible pairs, and the minimum of those gives you what we call the minimum Hamming distance of the code. Okay, and this is critical because it determines the error correction performance of the code. For instance, the parity scheme has 2. The parity scheme has a minimum distance of 2 because any code word will differ in 2 bits. When you switch one of the bits, the parity bit will also be switched, so they will automatically be different in 2 bits. So when a single bit error occurs, the result is not a code word, and in this way we detect the error. But the corrupted word is equally close to at least 2 code words. Okay, the Hamming distance between the legitimate message and the corrupted message is 1 in case of a single bit error. But also there is at least one other legitimate message whose Hamming distance is also 1 to the corrupted message. This is the reason we cannot decide between the original correct message and other candidates. We do not know in which bit the error occurred, and this is the theoretical explanation behind it. It falls in this Hamming distance space exactly at the midpoint of multiple legitimate code words. So we cannot really decide whichever should be the decision. The repetition code on 1 bit, remember, I take 1 bit, I repeat it 3 times. This means my minimum distance is 3 because my only code words are 0, 0, 0 and 1, 1, 1. Okay, so their distance is 3. So I can correct single bit errors. Why? Because when there is a single bit error, the difference between the corrupted message and the original correct message is 1, but the distance between the corrupted message and the other legitimate code word is 2. For instance, 010 has a distance 2 to this one. So I will decide on this, which means I can detect, not only detect, but I can correct single bit errors. But when the error is in 2 bits, then you approach to the other code word more than the original correct code word, so you make a mistake in detection. Okay. In general, this is a theorem. I'm not going to prove this, but this should be evident to you on this discussion. A code with the minimum distance equal to 2k plus 1, you can detect 2k or fewer bit errors because the result will not be a code word, but you can correct k or fewer bit errors because if the minimum distance between two code words is 2k plus 1, then if the error is more than k bits, then the corrupted message will approach an incorrect code word more than it departed from the original one. So you just stay below the midpoint so you can correct k or fewer bit errors.